and share screen. Awesome. Thank you everyone for joining us. This is Deep Learning Adventures and Fun and Engaging Meetup. You can find us on Meetup under Deep Learning Adventures. You can also find us on YouTube. If you search for Deep Learning Adventures, you can find our previous recordings. All our sessions are recorded, including this one, and will be posted tomorrow. If you're joining us for the first time, welcome. To give you an overview, we've been taking a deeper dive into what is called Kaggle courses or Kaggle Mini Courses. These are very short, self-contained modules on topics in data science in general, not just machine learning and deep learning. For example, we've covered like Python, data visualization. We've covered machine learning as well. A short introduction to deep learning, feature engineering, SQL using BigQuery. Last few sessions, we did a little bit of data cleaning and geospatial analysis. I enjoyed both of them. For the geospatial analysis, I actually ended up using some of the work that we did here at my organization at Noking Hungary. So it was really interesting. I like that approach of visualizing, heat map, choropleth, different markers, and how do you basically show, what I had to do is show demand and supply for some of our metrics. Today, I'm joined by my great friends, Robert and Dimitri, friends and colleagues and co-organizers. We'll be talking about micro challenges in Kaggle. And while I do that, let me also share a few links with you so that you can join us on Slack if you want, or you can also join us on YouTube as well. If you don't have any dinner plans or if you don't have anything else going on, we're actually hosting what is called a Friendsgiving after this meetup at 8:30 p.m. Eastern. It's a little bit late for some of us, but it's a little bit early for some of us on the West Coast. So it'd be awesome if you could join us, let us know. It's 8:30. The link is on the meetup as well. Cool, with that said, I'm gonna hand it over to my great friend Robert to talk a little bit about the first micro challenge. And let me stop sharing and enable sharing.
All right, can you see my screen?
Yes.
Yes.
Perfect. So this challenge was on the game of Blackjack, and the idea here is to write an agent for a player to optimize the agent's play against a dealer. And we're looking at a pretty simplified version of Blackjack. We'll go into the rules a bit later, but they do describe the rules right up top here in the notebook. So the basic idea is you have a player, maybe multiple players, and a dealer. And the dealer is dealt one face-up card, and the player is dealt two face-up cards. And as the player, you can keep asking to be hit with another card as many times as you like. But the limit here is that if the sum of your cards goes over 21, you lose the round immediately. And if you haven't lost the round and you've decided to stand on some number less than 21, then the dealer keeps drawing cards until he either has exceeded 17 or until he has exceeded 17, in which case he will either have simultaneously passed 22 or greater, which is called a bust, and he goes out and loses, or he finishes with somewhere between 17 through 21, and in that case, the scores are compared. So another aspect of this game is that aces can count as either value 1 or 11, depending on whichever is most advantageous to the person holding that card. So typically, you're calculating a total for the player. You're going to assume the ace is high until that ace gets too high and would be a bust, and then you can drop that value back to 1, and you still have another chance to get a better score. So in this micro challenge, what they're asking you to do is basically redefine the function should hit to be a better player. Right now, should hit is always returning false, and false is the don't hit me case. So you are, regardless of your first two cards, you are standing in place. So we define that here in the function, and I'll just kind of run this whole notebook as we go through it. While working on this exercise, I guess as soon as you get past a little bit, it prompts you with another message, so I constantly have to close that. So here's just some Kaggle setup code. Then they give you a little engine here. Blackjack, simulate one game. Player starts with just total of 4. Dealer starts with 10. Player decides to stay, even though that's a really bad choice there. And dealer wins 17-4. So they also give us a little tool to simulate a whole bunch of games. You can do n games, 50,000. Takes a few seconds to run. And then rather than showing all the cards, it just says which fraction of them did you win. So the purpose of the exercise is to redefine this function should hit in order to improve your performance. So, and that is actually the end of the micro challenge. Like they provide no more cells, no more topics of discussion. So everything else below here in the notebook is what I added. So I'm just gonna, here's the original function just to remember, we're just returning false at all times. So a few ideas that I wanted to explore, some of which we don't get to in this notebook, others of which we kind of beat to death. But we'll start with a simple decision threshold. Just look at the player score and decide, if you're above a certain amount, stand. If you're below that amount, hit. And I looked at trying to calculate an optimal strategy analytically, basically through solving a system of equations. And we'll show that in a fair amount of detail. One thing that I thought would be really interesting but didn't get to was designing just a simple perceptron. You could code it from scratch, basically, with a single hidden layer, maybe just 10 nodes or something is what I was thinking, and adjust the weights in that perceptron just based on the outcomes. If you win the game, no need to adjust. If you lose the game, then adjust in the direction of a gradient that you can define within the perceptron. And card counting. And it turns out that for this particular implementation of Blackjack, card counting won't do you any good. And I'll just show that later. Let's see if I can get to, okay. So a few extra imports. So just a little bit of exploration, see what the interface looks like. We'll run a few games. Looking at random seeds from 0 to 9, game 0, player starts with a certain amount, gives you what the dealer starts with. Player is always staying, remember? And dealer hits and receives 2, dealer hits and receives 6. The rule is that the dealer always hits until he has 17 or greater. So even on 6, he continues to hit. Then when he receives 10, he goes too high, busts, and the player wins. So sometimes this strategy of the player not doing anything at all can pay off. In this case, player ended up with a pretty good hand, but even if the player were down at 4, you might still have won. I think we see that in game 2 here. Yeah, player starts with 5, player stays, dealer hits a few times, busts, and player wins with just 5. So a few special rules that are different between our game and what you might find in a casino. There's no distinction between blackjacks and other forms of 21. So in this case, we have a player that started with ace-jack. That should be a blackjack, and the player should win unless the dealer also gets a 2-card blackjack. But in our implementation here, the dealer is able to win. The dealer, I should have mentioned, the dealer always wins ties. And the dealer with a 3-card 21 is deemed the winner here. I think at most table versions of this game, the 2-card blackjack beats 3-card 21. A couple games where he's showing that the player's strategy really is not optimal. You stay on 11 in game 7. Dealer won 18-11. On game 8, you're staying on a 12. And in both of those cases, it looks like if you had hit, there's a decent chance you might have won. Dealer strategy is also not responsive to the player, and you can think of this as being in the casino, the dealer might be playing against multiple players at a time, and often they have set rules, and at the tables there might even be posted exactly what the dealer is doing. So the dealer really has no agency over how to play. So on this one, this was a reference to a movie version of Blackjack, in which our hero Austin Powers stands on 5. I don't necessarily care to take the minute and show the clip, but it's kind of amusing. You can watch it if you like.
Cool.
And this is really the same thing. We're just looking at the same 50,000 games, I think. But we want to see here. Right. So this is a binomial distribution. We're just looking at games. They're either win or loss, Boolean output. Assuming that this is roughly the correct win probability for this particular model, then we should expect that in any other sample of 50,000 games, you might get variance or a standard deviation of plus or minus 100, 110 games or so for that model.
How does that translate? Does it have any meaning, Robert?
Does what have meaning?
The standard deviation that you're looking at here, or you just...
So I think that you would expect, if you run Blackjack Simulate for 50,000 games and keep hitting this over and over again, you would expect that to be the standard deviation of your win rate, or of the number of games won. So for 100, if you add 100 to the games that you already won, that would be just 19,100, and you'd still be just a hair over 38%.
Mm-hmm.
So showing that the numbers are statistically significant.
Okay.
So the first thing I wanted to do was look to see, okay, what happens if we choose just a single threshold based on the player's score. So this is pretty easy to start playing with. I just defined a threshold should hit 11. Simulate another 50,000 games. And we have a win rate of 41% already, with a strategy that is obviously not too high, because the player total has to be at least 12 before you're at any risk of busting whatsoever. So it shows that you gain about 3% and you're 1,500 games higher than you were. So it's definitely a significant difference there. Now, I guess one could point out that it's the same seed at the beginning, so it somewhat dominates. However, because of the different strategy, you end up with different cards dealt to the players after the first game anyway. Try another threshold, 15. So I wanted to test a variety of thresholds using this type of function, but if you look at what's happening here, I wrote the threshold in hard-coded. So I thought, well, it'd be awfully nice if I could make this a little bit more efficient and not hard-code it, but pass it in as a parameter. However, this should hit function and its method signature has already kind of been defined behind by Kaggle. So question is it worth trying to do that? So first thing I thought, well, you know, maybe I can just send a parameter, something like this, and try simulating again. Interestingly, this is the exact same result that we had with the naive model, even though, you know, the default threshold that I tried to pass it was 11. So clearly I'm doing something wrong here. So we define should hit. What did I do on this one?
You're printing it out?
Just printing it out, that's right. Using the threshold, Okay, so now the threshold, the default value is not what's being used, and it's just passing zeros or ones. Interesting. Let's see what happens when I try to add a fifth argument. And run it. And an error. So unexpected call signature for player hit. Did you add or remove parameters? Well, it certainly did. So what exactly is happening here? Why is there a 4-argument version of this thing, but 5 isn't taking? So I'm looking a little further and just look at the 3-argument version and print them, see what's getting passed in, and run a couple games. We'll look at those in a bit. I'll do the same thing with a 4-argument version and run the games again. And just to compare them side by side, I actually made an image down here. So with a 3-parameter version, we get to player starts with 5 and ace, total 16, dealer 10. Okay, the arguments passed in were player total 16, dealer card value 10, and player aces 1. Okay, so there's an ace here. Player hits and receives 4, 20. Now with the next time it gets called, 20, 10, 1. Oh, it looks like it makes sense. Let's look at game 5, and you can start to see something a little bit funny going on here. Player starts with ace and 6, total 17. Argument passed in 17, 10, 1. Player hits and receives 7. Total is now 14. So what you're doing is you're correcting for that ace that went out. Now you're going back to 14. But what's interesting here is that you still have a 1 in this aces column. So if you were going to use this aces column to determine whether you're on a hard 17 or a soft 17, or a hard 14 or a soft 14. By the way, I should define those terms. A hard 17 is one that is made up of cards that cannot drop in value. So if you get a 5 on a hard 17, you will bust. And a soft 17 is a 17 that includes at least one ace that is being used as high, so that you can take a card value 5 or higher on a soft 17 and you're still safe. This is what happens here. However, the parameters passed in will not tell us whether we are on a soft value or a hard value. All they're telling us is whether we have an ace. And now that we've used that ace and made it low, we really should treat this as though it's a soft value. So a bit of a bug actually with the software as written. So looking at the 4-parameter version, we have a very interesting thing going on here. So the player total 16, dealer card value 10. But if you look at it, now all of a sudden that we threw in an extra argument, the parameters are flipped. The dealer card value is first. The player card total is here. And we've got 2 things at the end here, 0, 1, 1, 0, 2, 0. If we look at this carefully, we can figure out that this is actually the number of low aces and the number of high aces. So this 4-parameter version is actually useful in that we would be able to distinguish these 2 cases and make a better decision based on whether the ace is being used as low or high. So I think I covered most of these observations here. Yeah. So now that just kind of piqued my curiosity, and I wanted to dive in and see how exactly the simulator is working. So now print Blackjack.
To beat the house, you need to know how the house plays, right? Is that what's going on here?
Exactly.
You're going undercover.
Going undercover.
The source is on GitHub, I think. Yep, the source is on GitHub of the simulator, so you can take a look as well.
Yeah, and we'll do that in a couple minutes.
Awesome.
So it's a problem view object, and this is actually the same type of object that we've been encountering in other Kaggle courses, which all inherit from this problem view class. And if we look at blackjack.dir, I was expecting maybe I'll find the simulate and simulate 1 game options, but I didn't see them. Blackjack simulate is actually a bound method of not a problem view, but a blackjack problem object. So maybe the simulate methods are in there, and we do find them in here, simulate a game. So there's the two reasons that I want to dive into the code here. One, the existing interface doesn't give any opportunity to customize threshold the way that I wanted to do originally, pass in an extra parameter. And two, you actually don't get any outputs from your blackjack runs except the simulated game parameters. I thought it might be useful to do analyses to look at the distributions of the dealer scores, the player scores. I won't end up using these at all, but I do end up modifying the code to output these things. So you can find the Kaggle Learn library on GitHub. And my thought was to make the interface a little bit better, fix those two things. I'm going to run a few little cells here and not talk too much about them. This is the code from the problem object, which I think I just commented out. Then we have a coding problem class, which originally inherited from problem. And I realized that for my purposes here in this notebook, I could bypass that inheritance and make things a lot simpler. Defines an interesting property down here, injectable variables. So coding problem, cccp.var. The coding problem always has a property up top, _var, and that _var is what is actually going to be used to interface with our should hit function, remember, that we have in our workspace here. What's going to happen is _var, in this case, is going to be a string that is should hit, and that's going to point to that object, and the engine is going to figure out how to access that method directly inside the classes that it defines. They're also going to use a decorator called injected, which tells you, given a method in the class, whether or not there are any arguments injected on top of it. So now getting down into the blackjack problem, we have, I should probably be running these cells.
If they're already run, I think you can just move forward, but if you need to run them, then go ahead. I want to get to your strategies.
So, right. So the injected, so there's some interesting coding tricks with decorators going on in here that I could use brushing up on. So it was good to look into it. That shows you the methods for simulate one game and simulate. Here's the actual code for the blackjack class. And we have, so I've just copied it and I'm running a blackjack problem now. And it's the same one we looked at before with seed 2. And we'll look at this one before with 21 beating, I guess it's a different one. Anyway, we can see that we have now basically duplicated the blackjack coding backdrop into this notebook. So we can go back and look at should hit, and we can use that one instead of the one that Kaggle is providing through the notebook. So now we're going to actually parameterize should hit. And I had to redefine the blackjack class for a couple of reasons. I'm going to define here a naive stand method, a naive hit strategy, and I'm going to be able to just call these directly. So player agent, the default is going to be my naive stand function. Player agent being originally their code was passing in this injectable variable to always point this to should hit, but now I'm running it a different way. Another interesting thing to note here, the deal method, return random choice, list range 2 to 11 plus ace, jack, queen, king. So what we notice here is that we're actually drawing cards with replacement. And so effectively we're playing with an infinite number of decks and there's no autocorrelation from one draw to the next. So what we can see here is that for this particular simulation, there is no advantage ever to be gained by counting cards.
So you can get more than 4 aces? Is that what it means?
Yeah, it's just as possible to draw 8 aces in a row as it is to draw the sequence 2, 3, 4, 5, 6, 7, 8, 9.
Cool.
What else is interesting here? So they have a couple of properties: player total, dealer total, calculating card total. Those I actually threw in later. Player hits. This actually looks like my own updated version of it. I guess it is. This is the one that I modified. So the strategy is implemented down here under player hits. And first of all, it's got to look at its own instance, determine what the player total is. Ace is low, ace is high. And it's going to eventually pass these into the phit method all through keyword arguments. So let's see, is there anything else important about what I did to modify this? I ended up, it was a little bit difficult to modify the property and calculation of card total directly, so I just ended up defining new ones that I would call only when I needed 3 outputs instead of 1. You could look at my Kaggle notebook for more details on that if you'd like, but I'll move on. So now I can just call Blackjack with the naive stand being my strategy, and didn't define it, so I didn't run the last cell. And it's going to play the game, and it's going to output the outcome, player score, and dealer score. So we'll modify Blackjack problem a little bit to be compatible with the new outputs. We're going to be outputting wins in a matrix. We're going to be outputting the scores for each game. We're going to be outputting the dealer score. And we're also passing in keyword arguments a little bit differently here than we were in the original code. Just run that. And now what we can see with our outputs, we get a Boolean, whether the player wins, and then 4 losses, and then the scores at the end of each one. We could use that and do more analysis on them if we like. I'm also going to define a threshold strategy here now so we can actually run the question we originally wanted. And I'll look at, let's see. First of all, we're going to compare these 4 strategies. Threshold strategy without keywords is going to be using 12 as a threshold. But threshold strategy with keywords, you just pass the keyword, the way I designed it, you just pass the keyword in as an extra argument to simulate one game. And that will end up getting passed to your strategy function.
And I'm sorry, the threshold, is that 12 standard deviations when you're setting it?
No, so that I'm just choosing the player score. I'm only running it based on the player total. So if the player has cards totaling less than 12, what this is going to do is hit.
Okay.
And if the player has cards totaling 12 or greater, then this will return false, which means stand.
Oh, okay. I got it.
So the function that the Blackjack class is expecting is true on hit, false on stand. So we can run down through these 4 examples that printed out here, and we'll be able to see that our strategy actually did implement exactly as expected. I'll move along though, and we can run now for all these different thresholds. I won't stand here and watch it, but it will show that 14 is the best score that I get, or the threshold that gives the best score from out of these thresholds. We get 41.8% on that. And the other ones, it's kind of a concave function as you'd expect. It drops a little bit more the higher you get. So what I really wanted to go into then was, this is a simple enough problem that you can actually solve it analytically, especially given the fact that we found out that the cards are being drawn with replacement. So there's really only one distribution of cards. You have 1/13th chance of every value at any draw. So and then it's pretty simple. The dealer decisions are all deterministic, and there's not that many total states in the system. So the first thing I wanted to do was compute the probability distribution for what the dealer's final score is. If you recall the dealer's rules, he has to hit whenever he's 16 or below. And if he's 17 or above, he stays. So there's only 6 possible outcomes the dealer could have: 17, 18, 19, 20, 21, bust. So I'm going to define 2 probability distribution functions, and these are going to be matrices of data frames, actually. We're going to have on the rows are going to be the 6 dealer outcomes, and in the columns is going to be the current score, the dealer's current total, and this will be accessible anywhere in mid-game. So we'll be solving this a little bit like if you're familiar with dynamic programming, where you can iteratively generate solutions based on problems that you've already solved. Here, we're going to be stepping backwards from final scores to eventually find conditional and marginal probabilities for the starting position. It's conditional probabilities for any given score and marginal probabilities for the starting position of 0. So just to give a little better idea of what we're looking at here, what I've done so far is just filled out the end game states. So if the dealer has 17 currently, he will finish with 17. If the dealer has these scores currently, he will finish with those. And if the dealer has these scores currently, that will count as a bust. And this is for the case of no high aces, and a separate array for the case where you do have high aces. You're still going to stop here, but now we can go back, so we're going to have to compute these ones. So we filled in all the things that we know are 1. So how to fill in the other ones? You can actually write out recursion relations and get an entire linear system of equations that will be invertible with exactly a single solution. But because of the iterative nature where you can step back here, you can actually just solve each one at a time. So the next few cells, I'm going to do that, starting with a score of 16. So what is the probability, given a current score of 16, what is the probability that the dealer ends up in each of these buckets? 17, given a current score of 16, if you draw an ace, you'll get 17 and end. If you draw a 2, you'll get 18 and end. 3, 4, 5, and 8 times out of 13, you'll draw some number too big that'll put you in the bust category. And once you've computed 16, then you can run the same for 15, where you're accessing these guys, but you also have the value for 16 comes into play if you draw an ace on 15. So you just iterate those back. Now that you've done the calculations for 11 through 16 in the case of no aces, now you can figure out what the probabilities were in the case of where you needed to convert floating aces, high aces. So now for the ace data frame, we can fill in probabilities of ending at each of the 6 outcomes for each of these high scores, including a high ace that has to drop down low as this result is reached. We can continue iterating backward in the aces data frame after we've computed the 22 through 26, all using the same recursion relations. Finally, we can use the same types of relations to fill in smaller values in the original dealer array. So we get all the way back to 0. And in the 0 column, you actually have the marginal probabilities of the dealer reaching any of these outcomes, not conditioned. But in every one of these other columns, you have the dealer's final result conditioned on that first card being drawn for 2 through 10. And if the first card is an ace, well, in that case, you would want to look in the PDF dealer A array at 11. So going on a little bit further, I just did a couple of sanity checks here, and to determine that, yes, we're getting the marginal distribution actually is the mean of the conditional probabilities. So that's a good sanity check there. So this is now the marginal distribution for the player's probability of winning if he stands. So if he stands on 21, he's going to win 88% of the time. If the player stands on smaller numbers, you're going to win less and less percent. These are all equal because we know that the dealer will only ever keep hitting through these numbers. So you're only going to get, the only time these ones will ever win is if the dealer busts. So this next array here is what is the probability of the player winning given standing on a particular number. So the rows are player reached a certain score, should the player stand, and the columns are what is the dealer showing with his one card that's face up. And another sanity check where these two marginal equals conditional mean. At this point, you can generate an entire matrix of what is the, now given that a player hits in a certain condition, what is the probability of winning the game. So we already saw what is the probability of winning the game if the player stands. Now we want to find what is the probability of winning the game if the player hits. And again, just generated using similar recursion relations through all of this. Compare it to player stand. Eventually what we're going to do is, this is going to be our decision matrix. If the player has a current score, 12 through 20, and the dealer is showing this value, we're going to hit where it says true and stand where it says false. And we want to do the same thing now in case the player's hand includes a high ace. We're going to have a different table. And those are the probabilities of winning. We need to compare it to the probabilities. These are the probabilities of winning on a hit. We need to compare it to the probabilities of winning on a stand. And for the case where the player has an ace, you're much more likely to hit because it's almost like you get a second chance at not busting. So see, I just made that data frame a little smaller. Now the payoff at the end is I'm defining another strategy function, analytical strategy, with taking these same keyword arguments that the Blackjack function is going to provide us. Player total. So the strategy here is going to be if the player total is less than 12, always hit because you never have any risk of bust. Player total is greater than 20, never hit because if you're at 21, you can't possibly improve. We go down here, and the mechanism we're using here is if the player has a high ace, we're going to look at table player HA, compare its value to player S being the probability of winning standing in that situation, probability of winning hitting in that situation, return true if probability of winning on a hit is greater than the probability of winning from standing. Same is true for the case where you have no ace. And just simulated another 50,000 games there. And you get a win rate of 43%. So all that for just a small amount, but I think that is actually optimal given the parameters of the problem as defined. That's all I have.
3%. Cool. I know that our next colleague Dimitri has to go up early today, so we're actually going to skip, or not skip, we're going to postpone his session for another time. We can take the next 15-20 minutes to talk about your approach, Robert, and I can share also my notebook as well. Dimitri, is that okay with you?
Yeah, absolutely.
Yeah, sorry, Dimitri. We'll definitely need to reschedule because that's also a very interesting micro challenge. And
sorry about that, Dimitri. I didn't realize there was you were going to take off.
No, Blackjack is much more exciting than airline pricing. So.
Perhaps, but the airlines do leave on time, so we can't delay you.
I want to share my approach real quick, and I want to go back to your approach if you don't mind. But before we do any of this, I saw some questions on the chat.
Yeah, I've been ignoring the chat. If
you have any questions, feel free to unmute yourself. There were some questions on how many decks you have. It looks like we don't have a specific number of decks, right?
Well, it's an infinite number of decks effectively, given that we're drawing with replacement.
And another question I had for you, Robert, is are you able to keep track of what was your previous card? Because in the current code, I'm not able to keep track of, or maybe are you able to? And do you have access to all the cards that you've been dealt so far?
I missed that. Can you say that again?
Do you have access to all the cards that a player has in front of him or her right now? No, right?
Do you have access where?
In your what is your method called?
In my strategy?
In your strategy function.
No.
Right.
So the variables passed in are player total,
Mm-hmm.
which is just the total showing value, and this is going to be 1 or 0, which is whether the player has a high ace.
Mm-hmm.
There was the other parameter player low aces, but that turns out to not be helpful.
So to bypass the hard and soft scores, do you have to have 4 parameters in the code?
To bypass the hard and soft scores, do you have to have 4 parameters? I'm confused.
Yeah, because back a while ago, you showed us where the parameters flipped.
Yeah. So I
Was
think
that-
what happened there was they had multiple versions of this code, and if you dig around in the code, you see various switches. If is legacy, do something, and otherwise do something else. And I think that at some point there was a 4-parameter version that they were using, and they eventually dropped it down to the 3-parameter version for this notebook.
And so how did you figure out the problem of dealing with the high and low A's?
How did I figure it out, or how did I solve it?
How did you solve it?
So what I did was for the analytical case, when you think about it, an ace is at any point either value 11 or value 1, and it will be value 11 if that gives you a total that does not bust. Otherwise, it will be value 1.
Okay.
So the fact is that this problem, because we can't card count, since we're drawing with replacement, there's no advantage to be gained by looking at the cards we have in our hand, other than what is the total, and does it include any ace that we can turn from high to low. And you're only ever going to have one of those, because if you had 2 high aces, you'd already be busted.
Right.
22.
22.
Right.
So it turns out that those couple of parameters, the player total, what the dealer's showing, and whether or not you have a high ace, turn out to be, I believe, the only 3 conditions in the current state that are useful.
Okay.
Robert, your 2 matrices that you created, can you explain to them again? Is that like a probability distribution based on simulated games, or is that just based on the fact that you're drawing cards randomly and each one of them has the same probability of being picked up?
So it's the latter. It is entirely calculated, nothing entirely calculated from the known distribution that any one of these 13 card values is equally likely to appear on every draw.
So you start with the 0-1 matrix, which makes perfect sense. If you're on 17, you stay on 17. If you're on 18, you stay on 8. Basically, if you're more than 17, you stay. If you're below 17, you hit.
Yeah, this was the initial seeding of this matrix, which I'm going to
Okay.
fill in with probabilities as we go down.
And the O and the A matrix was for the low and the high aces. Is that what you mentioned when you use the ace as a 1 or the ace as an 11? Is that the difference?
Did not. Can you repeat that question?
The difference between the two data frames is when you use what you mentioned as a soft or a hard ace. Is that what it is? Okay, perfect.
Yeah. So
Then,
PDF dealer A is assuming that the dealer has at a given time a hard or an ace showing as high.
from these two matrices, got it. So what is the difference between these two matrices? Only the bus case?
Yeah, if the dealer is showing a value of 22 plus and that value doesn't include any aces, then then the dealer has lost. If the dealer is showing a value 22 plus, but there's an ace in there that was being counted as high, then what I did was I said that PDF dealer for a score of 26 must be the exact same distribution as PDF dealer without ace 16, because you're looking for the probability that you end up in each of these 6 buckets at some point after this whole table is filled in and you've completed the game. You have to end up in one of these states. And so if you are at, if you look into the recursion relations, the only way you can get to 26 here is if you were on 16, you had an ace somewhere in your hand included in that 16. So maybe the dealer had 5 and ace, and then drew a queen or something that would put you to 26. And now you don't lose the game, but instead you jump over to this table instead and counting that ace as a 1. So you're back here on the 16. So this column will equal that column. So after I filled in these 6 columns, 11 to 16 here, I could complete those columns.
Got it. Then what equations did you solve to fill in the rest of the table?
So I don't actually show the equations other than kind of in the code, but what you can imagine is that on 16, if you're on a hard 16, so no aces, you have a 1 in 13 probability of ending up on score 17. The only way you get there is if you draw an ace. This is 1/13th, 1 in 13, 1 in 13, and 8 in 13 for the last one. So, and you've done that you've filled out column 16 just by looking at the 10 columns to the right of it. And you can see that's kind of what's happening here in the code. You're doing for a given score, starting with 16, you're referencing scores 17 to 26. And then 3, this is for the face cards over here. You put extra weight on that one. And then once you've done 16, now we have enough information to compute 15. So we go back through and we're going to use 16 through 25 there. And once you've done 14, you have enough information to compute and so on.
So if I read this, let's say an entry of this table, of this matrix, you're at 16 and you have 0.07. That's not 113, I guess. Or I don't know what that is, 0.07. Does that mean that that's the percentage or that's the probability you're going to stay?
So the probabilities in this table are the probabilities. This is the dealer. What we're doing first of all is trying to figure out, given the dealer's current hand, what is the likelihood of the dealer ending up in each of these 6 states?
Got it.
So we've computed here that if the dealer is currently showing a hard 16, the chances of ending up in each of those 6 states are as follows.
Got it.
So if the dealer is currently showing a 15, the chances of ending up in that state. And the power of this method is that, it's a little bit complicated. A typical dynamic programming problem, you might just be able to iterate all the way down, 16, 15, 14. But here, when you get below a certain number, then you start having to look at the other table with the aces.
So if you scroll a little bit to the left, that's what I need to see, your index. Is that the 17 perfect?
Yeah,
18, 20,
but the beauty of this is that once you've gotten all the way down to 0, that is your marginal distribution, like the probability of the dealer ending up from scratch, because the dealer always starts with 0. You always begin with this state. And and each of these other ones in here is a conditional probability or a conditional distribution based on currently being in that state. So if the dealer's showing card is a 7, then all you have to do is look at this column after it's computed, and you'll have the conditional probabilities of the dealer ending up in each of these states.
Okay, so now you have this table. How do you use this table to imply it, to change your strategy? That's the last piece.
So I kind of blew through this. I showed how to compute some of that stuff, but what you're going to do after you've computed the dealer's probability distribution, the next thing you want to do is, what is the probability, now that we know every score the dealer could end up with and the probability of ending up at that score, now we can compute for a given player total, how often would that total be sufficient for victory?
Got it.
So that's what we're looking at here. This is the player marginal distribution of standing. Given knowing nothing about the dealer's condition, not before we've conditioned on any cards, the player has a 28% chance of winning if he or she stands on a 12, and an 88% chance of winning for standing on a 21.
Got it. And the next step is to condition it on the dealer's hand?
Yeah, so now what we want to do is condition on the dealer's hand, and that's what this matrix is. And it's interesting because if you look at it kind of closely, you'll see that your probability of winning is pretty high for standing if the dealer is showing a 5 or a 6, and it drops precipitously if the dealer starts showing a 7. So why that is, it's because the dealer has a high likelihood of drawing a face card or value 10 on 7, in which case you'd stop on 17. The dealer chance of busting is much higher from 5 or 6.
Explain to me the significance of the columns and the rows here. Is this from the player's perspective or the dealer's perspective?
This is from the player's perspective. So the columns are a card being shown by the dealer, the one value card that we see. And the rows are what the player's current total is.
Oh, got it.
And I ignored everything below 11 because you always want to hit on that, so it wasn't necessary for computing strategy.
So if I pick, let's say, a random cell here, if a dealer has a 6 and the player is sitting at 12, he has 42% chances of winning. Is that I interpret it?
He has a 42% chance of winning if he stands on 12, yeah.
Got it.
So this array is, I mean, it's almost as if, there's no difference between a hitting and getting a 5 and hitting and getting a 9. Based on if the dealer was showing a 6, it's all 42% chance up until.
Yeah, you'll see that everything, these rows are identical from 12 to 17. Because the dealer will never stop with a score between 12 and 17.
Oh, okay. I had that. Okay.
Sorry, the rows are what the player has or what the dealer has? I thought
the rows are what the player has.
Okay.
But after the player makes the decision whether to stop, then the dealer will start drawing cards.
So do you think that, from 12 to 16 to actually 12 to 17, that number is all the same, the probability? Is that just because of the infinite nature of the decks?
So if we had a finite number of decks, then you could definitely have conditioning that would change these numbers. That wouldn't, that on its own would not make these different though from one row to the next in here. Just
Okay.
because the dealer is never gonna, the only way that a player could fare better with a 13 than with a 12 is if the dealer stops on a 12.
Oh, okay. Yeah.
Basically, the dealer doesn't do anything until 17, right?
Yeah, the 17 is the smallest number a dealer will stop on. So, and since you don't win ties, 17 doesn't change from the previous one either. But if you stop on 18, you not only beat busts, but you also beat dealer 17s now. The player stopping before 17 is banking on a dealer bust because that's the only way the player can win. With a score of 17 or below.
Yeah, I have a very simple question for you. The dealer has a strategy that he doesn't stop until he sees 17 or more, right?
Yes.
If the player uses the same strategy, shouldn't you think that the win ratio would be close to 50%?
Well,
I tried and it wasn't.
Right. So the problem is twofold, but mainly the fact that the player both doesn't win ties and has to go first. So if the player busts, it's over regardless. And ties always go to the dealer.
The player has to go first, meaning what? What do you mean? I mean, he has 2 cards first?
The player has to keep making the hit or stand decision and stop on a number. And then the dealer starts taking cards based on this algorithm that has been determined.
Sure, but I mean, using, to me, they're 2 independent agents. The cards they draw are from the same distribution. So I would think it would be 50-50. I don't know why it's not.
I mean, the probability of a tie is pretty high.
Okay, fine, but it's that high, like 10% high? Like, yeah, I mean.
Yeah. I mean, the value of a card is only 10. The maximum value of a card is only 10. So if they each adopt somewhat optimal strategies, the chances of either both of them busting, which doesn't actually happen because the dealer doesn't go if the player busts, or them both finishing on the same number is probably 14-15% or so. I mean, if you look at the player's probability of winning on a 21, even, it's not even 90%.
But typically you get your money back.
So that was one of the simplifying aspects of this problem, is that all we're looking at is wins and losses. We're not weighting anything differently by how that happens.
Cool. Thank you, Robert. This was super, super interesting. If you don't mind, I'd like to share my approach.
Sure. Yeah, I hope it wasn't too difficult I know we're just kind of looking at numbers, and I didn't take the time to try to make it a little bit more visualization friendly.
Yes, I enjoyed it. Share screen. So what I did is, I'm just going to look at the report here. I tried different strategies as well. So the first one is called 2 cards, and that's basically you stand on 2 cards. That's the benchmark strategy that we saw. The other one is I did some kind of similar to you, Robert, like some kind of a grid search where the method didn't allow me to try different thresholds. So I just manually tried different numbers, and I said, if the player total is less or equal than a threshold, then what is the probability of winning on those 50,000 simulated games? And you see this 8, it was 38%, 9, 10, 11, 12. So the max I got was about 11 or 12. I got 41.9, 41.8. if my hand is less or equal to 11 or 12, then I hit. That's what it means. This is hit. Yep. Let's double check. Yeah, so that was strategy 1. If I'm less than a threshold, then hit, otherwise false. The next one is kind of like the opposite. If I'm above a threshold, so I'm looking at like coming from the left. The other way to look at it is if I'm, well, let's see. So basically I hit if I'm less than 8, 9, 10, 11, 12, 18, 16, 17, 18, 19, 20. Obviously 20 hit, you only get 15% because chances are you're going to get a large number. Then the opposite of it would be I stay if I'm more than this threshold. So I stay if I'm more than 19, more equal than 19. I stay if I'm greater or equal than 18. I stay if I'm greater or equal than 17, which is the dealer's strategy, right? So what in the world, 40%? And you're saying that equality is is robbing me off of that 10% chance of winning, if I understood you correctly. That if both of us get 17 and the hand goes to the dealer, that costs me 10% chances of winning.
So I'm not following what is different about the stand if player versus player total.
So player total is I request another card, I hit if I'm below this threshold. So if my total value is less or equal to 15, I'll ask another card. And if I do that, I will win 41% of the time.
So these numbers here are basically what I was computing with the thresholds. It's probably the same.
Yeah, different threshold, exactly, yeah.
But then what is stand if player doing?
So stand is the opposite strategy. I don't ask for a card, I stop, I stand. I stand if I have more than, if my value is more equal than 19.
Isn't that,
I mean, it's symmetrical,
is that
right?
kind of the same thing?
Yeah, I mean, it's kind of like symmetrical, I would say. So yeah, I stand if I'm more than or equal to 19 is the same as I hit if I'm less than
Or equal to 18.
Yeah.
Yeah.
And where's the 21?
So there's no. So 21, it's not worth exploring, right? 21, if you. So let's say this one. If I'm more equal than 19, then I stand. So that includes 19, 20, 21. As well as, yeah. So if I'm at 18, 19, 20, 21, I stand. If I'm more equal than 17, I stand. If I'm more equal than 10, I stand. But you see, if I do that, then my probability of winning drops to 38%. So there's like a sweet spot here that I should stand around, I don't know, 13.
But and then player total less than or equal to 21. Was there a probability that you calculated?
Player total less or equal to 21 means that I should ask another card if my total is less or equal to 21.
Okay.
Yeah,
Okay, got it.
which doesn't make sense.
Right.
Then another approach was I look at the dealer value and I look at my value and I compare how they relate. So strategy 3, let's look at the code. So I return true if the player total is less or equal than a percentage of the dealer total. So if my total is less than half of the dealer total, I ask for another card and I win if I do that 38% of the time. If I ask for another card, if my value is more or less the same as the dealer, I win 39% of the time. And the best value I got was I asked for another card if I'm less or equal than 1.7 times the dealer value. So that was strategy 2, strategy 3. Then I tried some other ones of combining if I'm below threshold as well as if I'm below threshold compared to the dealer. So player 8 less or equal than 8 and player less or equal than half the dealer means that both of those criteria are met. So both of them have to be met. I didn't get good of numbers there. Then I tried the or when either one is met, meaning, let's look at, for example, the last one, when either I'm less or equal than 16 or I'm less or equal than 1.5 times the dealer's value. Then I ask for another card. And if I do that, I win 40% of the time. So doing all this, the highest number I got was 41.9, I think.
Looks like 42.1 at the bottom there.
Oh, 42.1. Yep, perfect. So that's, so I ask for another card if I'm less or equal than 12, or if I'm less or equal than 1.1, the dealer value. But you got 43. The question is that the maximum? Is that the optimum? Over?
I mean, it seemed to me that we knew enough about the problem to solve it analytically. It's possible that I overlooked something, but I can't think of anything that would be inexact about, like, based on the assumptions that we're making and the very simplified version of the rules that we're playing.
Yeah. I have to say this, having watched Casino Royale, James Bond recently, and doing this micro challenge really motivated me to keep going. This is a scene from the movie. Another thing is, I don't know if you look at the forums, but the forums were really interesting. I shared my approach on the forums as well. Some other, colleagues here that have gotten 43. Let me see. Somebody got 39. Somebody got 50, but he said he used it.
I did look at that when you posted.
Go ahead.
I was gonna say, I did look at that when you posted it. Did you see the one where someone managed to get 100%?
Well, I've seen this card counting, but you said that doesn't help because you have unlimited decks. So I don't know how this guy got 50%.
Yeah, I don't know if they changed the code or something, but if you look at the engine that we were using, it was just pulling as if they were being replaced every single time.
Yep. So, yeah, I don't know how this card counting got in 50%. He created this similar to your approach, I think, right? This table.
Card in hand. So he's actually doing other strategies too. See the D's in there?
What is that?
These are variants on the game. The D is for certain places you're allowed to double your bet.
There's no betting here.
Other
Right?
places you're allowed to like split a pair. If you're dealt a pair of 4s, you can split them and do 2 separate hands.
Mm-hmm.
There's a variety of rules, and those are much more complicated tables for those reasons.
Is it similar to the table here? Okay, stand, double if allowed, double if allowed. Okay. So you're saying there's somebody who got 100%? Is that what you said?
Yeah, I thought it was pretty funny, actually.
I haven't come across that approach.
Not too far down.
55%. Really? Wow. Okay.
But I still think that they're clearly playing a different game.
You mean they changed the engine? Is that how they got probably, or are they? Where is that?
I don't know.
Is it on this page?
Yeah, it was on that page that you linked from the first time. It was amusing, but essentially what he did was just in the should hit function, reset the random seed, so he got the same hand dealt every time.
Oh. I found it. No.
So, somewhere in there.
Is it this one?
Yeah, that's it right there. Y'all are fussing over nothing. The best solution is 2 lines of code with 100% accuracy.
So you're setting the seed. Is that what's going on?
Yeah, like it's not even doing a strategy. It's just returning.
A random number? How is that giving you 100%?
Random seed, it's resetting the seed, and then the next hand you're going to get. It's preventing the random number generator from generating new games.
It's preventing from. So, but do you know the numbers that will be drawn already, or no?
I did notice that for random seed 0, the player does win. So if you can get that.
This is interesting. I mean, I like this. Thank you for finding it, but we're getting close to Friendsgiving.
Obviously, it's just cheating, but
it is. But it's
it
interesting, right? Cool. All right, friends. Any more questions, Robert?
They won 50,000 out of 50,000 games. Win rate 100% at the bottom of the screen.
I'll definitely take a closer look at this one. Cool. Awesome. All right, friends, we're getting close to our Friendsgiving event here. So yeah, take a break, get your drink or food, and hope you can join us in about 10 minutes. Thanks again, Robert. This was really cool. Thank you, everyone, friends. I'll post the recording tomorrow. Have a good evening. Bye, everyone.